Let's go back to our oscillation frequency. Remember, we got the result that omega prime squared was equal to omega naught squared minus gamma squared. Now what's the difference? Let's remember, what's the difference between omega naught and omega prime? Omega naught was the frequency that the oscillator would have, root k over m, if there was no damping, if there was no friction involved in the problem. Omega prime then is the oscillation frequency that the oscillator will have when there is damping, because the damping tends to slow down the oscillator, so rather than going quite as fast, it's going to go a little bit slower and stretch the waves out. Remember that gamma was equal to b over 2m, m the mass obviously, and b was directly from the damping force, which was the proportionality constant between the force and the velocity. So the bigger b, the more frictional force we have, the bigger b, the bigger gamma, and so gamma increases. Okay. Now let's think about this. When we have no damping would mean b equals 0. B equals 0 means gamma equals 0. Gamma equals 0 means omega prime equals omega naught. Okay, that makes sense. With no damping, the frequency of the oscillator is just the frequency of the oscillator with no damping. Well, yeah, okay, obviously, so good. We go to the situation omega prime equals omega naught with no damping. As b increases, what happens? Gamma increases. As gamma increases, omega prime decreases. So the more friction we have, the smaller omega prime. And what does that mean? The slower the oscillator. So say no friction, it maybe oscillates like this. With some friction, it oscillates slower like this. Omega prime gets smaller. Well, how big can gamma get? Well, what would happen if gamma were so large that gamma squared was equal to omega naught squared? Well, in that case, omega prime would equal 0, and we would have no oscillations at all. Okay, I'll come back to that in a second, but let's figure out what would the value of gamma have to be. For gamma squared to be omega naught, gamma would have to be gamma squared to be omega naught squared. Gamma would be equal to omega naught, and what would we have? We would have gamma equals b over 2m equals omega naught. In other words, b would have to be as large as 2m omega naught. So if we had so much friction that this coefficient b were as large as 2m omega naught, then we would end up with omega prime equal to 0. This amount of friction is what we call critical damping. And I'll write b sub c. This is the amount of, or the size that b would have to be in order to have critical damping. So what kind of motion would that look like? Well, let's go back to our plot of the slightly damped oscillator and see what happens. When we have a small amount of damping, in other words, where the damping coefficient b is less than that critical value, we end up with an oscillator that oscillates, but the amplitude, as we've seen, gets smaller and smaller, decreasing exponentially, like e to that minus gamma t. When we have critical damping, in other words, when b is actually equal to this critical value, b sub c, 2m omega naught, we no longer have oscillations. In other words, we started at some maximum initial amplitude, and it never passes equilibrium and oscillates back and forth. It just goes to equilibrium like this. Imagine if we had a mass on a spring, we take that and we put it into some viscous fluid. If we just did it in air, we would have, say, obviously underdamped. But we put it in some viscous fluid, maybe like water or something, maybe not too viscous, like water, we put it in and maybe it oscillates still, but eventually damps out fairly quickly. We put it into something more viscous and we pull it down and it just manages to come back to equilibrium, okay? Not too viscous, because we still can put more friction in here, and rather than being critically damped or underdamped, that would be overdamped, and we'll take a look at that next. But hold on one second. So for critically damped, that's just when we have enough friction that we no longer pass equilibrium, we no longer have oscillations, and the oscillator just slowly returns to equilibrium, basically exponentially. Okay, great. Now what happens when we have more friction than that? If we continue to increase b, in other words, continue to increase the amount of friction, the amount of damping I should say, so that B is greater than BC, then what happens? Well, then the oscillator returns to equilibrium, but even more slowly than the critically damped. We call this over-damped. Imagine now we put the oscillator in very, very viscous fluid, maybe like cold molasses or something. We pull it down. Then what happens? It comes back to equilibrium, but very, very slowly. It takes a much longer time to return to equilibrium, even than the critically damped. Now, obviously, the critically damped and over-damped actually never cross equilibrium, but they kind of get there exponentially, and underdamped gets closer than overdamped in a shorter amount of time. Critically damped. So, why is this important? How can this be used? Well, sometimes we have oscillators where perhaps we want the object to return to equilibrium. There are some simple examples, and one that I think is fairly an easy one to understand is, imagine you have a swinging door. So you push the door open, and rather than having a latch or whatever, it just kind of goes back and forth. If you have an underdamped oscillator and you push the door open, the door will just flop back and forth and back and forth and back and forth, and it'll take a long, long time to finally stop and come to equilibrium. If you have it overdamped and you push the door open, you push it open, and it takes a long, long time to come back to equilibrium like this. Well, if it's a doorway and you want to keep your house warm in the winter, or you want to keep it cool in the summer, you want the door to close as quickly as possible. You want to push it open and have it come back to equilibrium in the shortest amount of time to minimize the amount of air exchange from the interior and the exterior. Well, in that case, you want to put some kind of damper on the door to make it critically damped, and that will bring the door back to equilibrium as quickly as possible. Even if it doesn't swing back and forth, I'm sure you've seen doors that you push open and they have a little damping device up at the top that regulates how quickly the door comes back. If it's underdamped, then the door will slam close. And that'll close quickly, but it's kind of disturbing to have this loud slamming. And again, if it's overdamped, it will take a long time, but if it's critically damped, it will come back to close as quickly as possible. And yeah, it makes that noise. Yeah. Okay, very, very good. Now, there are certain circumstances where we want an oscillator to keep going. All sorts of different situations. Perhaps something oscillating in a clock, maybe a pendulum that is keeping the clock going, or something in a wristwatch. If it's, say, a digital wristwatch, maybe a little oscillating crystal or something like that. There are all sorts of different situations where we want an oscillator to keep oscillating. Well, how do we do that? Because there's always going to be friction. Even if there's a little friction, we know it's going to be underdamped, and eventually the oscillator will stop. How do we keep it going? Well, we have to apply some kind of forcing function. And I think the simplest example to think about is, imagine there's a child in a swing, and you're pushing the child in the swing. So the child is in the swing, and they want to keep swinging, so what do? You have to keep pushing them. You have to keep pushing them every time. If you stop pushing, eventually they will stop swinging. And they don't like that. They want to keep swinging, so what do? You have to keep applying a forcing function. Let's take a look at what that forcing function has to look like and what kind of response we get from the oscillator depending on what that forcing function looks like. Let's go back to the equation of motion that we were dealing with back when we started looking at the solutions for the damped harmonic oscillator. We had the d squared x dt squared plus b over m dx dt plus k over mx equals 0. And let's just remember what these things are. This was the acceleration. This was the damping term, the b times v brought over to the other side, but then we divide by the m from ma. This is the kx, that's the spring force, and the divided by m, and then all of this had to equal 0. So this is the unforced, or the oscillator without a forcing function. So what are we going to do to put in here to keep this thing oscillating? Well, let's think about it physically. Imagine again, you're pushing a child on a swing. Do you apply a constant force? So you push on the child and you apply a constant force, and eventually they'll come up to some height and you'll be stationary. You'll be in equilibrium. Your constant force will have brought the child up to some displacement, and then they'll stop. The force just keeps the child there. Basically, in that case, you'd have some constant value over here, some constant force. You've divided by the mass. And in that case, these terms would be 0, and you would have k over mx equals f naught over m. In other words, kx equals f naught. Basically, you come to a situation where you're in equilibrium. With a mass on a spring, you've stretched the spring some constant value, and nothing is moving anymore. Okay, well, that's not very interesting. There's no oscillation. So what are we going to have to do? Well, how do you push a child on a swing? You push the child, then you stop. You let them go and then come back. Then you push the child again and then you stop. Push the child again and then you stop. Well, rather than force, no force, force, no force, probably the best thing would be to have some kind of sinusoidal or cosine solution of the force. To have something that's going to look like f naught over m times some kind of cosine dependence. So let's put it in at some frequency, omega t, and that will give us the time dependence. Okay? There we go. So we'll assume that we have some forcing function, f naught cos omega t. And then we divide by m, and then solve it like this. Well, what's the solution of that going to look like? Well, I'll put it down, we'll take a look at it.